Example number 3. Now, this is the point in grade 11 pre-calculus where a lot of people's brains explode. Okay, the biggest thing that we need to remember is anything. So if I were to say q to the squared is always going to be greater than or equal to 0, always. If you put in a negative number into q, so if q is -5, -5 squared is +25. It's always greater than 0. Or if I were to put in a +5, 5 squared is 25, which is greater than 0. So you're always going to say a squared, so a squared number is always positive. And in addition to that, radicals with an even index, so this right here, there's an implied 2, remember? They're not defined when the value under their radical is negative. So what I'm saying is, for what values of x does this exist? So this is asking for what values of x is the radicand positive. So we said a squared number is always going to be positive. So x can be anything. I can put in a negative number here, I can put in a positive number here, I can put in an irrational number here. So I'm going to say x can be any value that is in the real numbers, not imaginary numbers. So all I'm saying is x is an element of the reals. Because if I put in a negative here, this will still remain positive. If I put in a positive here, this will still remain positive. So this is defined for any value of x. This one gets a little bit trickier because we have an even index here. So that means that the radical has to be, or sorry, the radicand has to be greater than 0. So we can just logically reason it. Okay, I know that this number, -12, is always going to be negative. So it means that I have to multiply a negative number by another negative number in order for this radicand to be positive. So I can simply from this say x must be less than or equal to 0 for the radical to be defined. However, some people need a little bit of extra steps here because they look at that and they're like, I don't even know what to do. So this is quick. This way will always work. So we're only doing this for indices that are greater than, that are even. So I would say, okay, so -12 x to the power of 3 must be greater than or equal to 0. I'm going to isolate the variable, so I'm going to divide both sides by -12. X to the power of 3, and because we're dividing by a negative number, the direction of the inequality switches. 0 divided by -12 is going to be 0. So x to the power of 3 must be greater than 0. I'm going to take the cubed root of both sides. So then I'm left with x must be less than or equal to 0. We come out with the exact same answer. For some people, you're going to just be able to logically reason to it. For some people, you need a few more tangible steps to work it through. Now, this example is kind of like the, the mothership of questions, because not only do we have to state where it's defined, we also have to simplify the radical if possible. So, first things first, let's state where it is, state where the radical is defined. So before we start messing around, it's always good to see where we can have answers. So I'm saying that this is 2, so I know that the radicand, so since index is 2, which is even. The radicand must be positive. So I can always say that any number squared is always going to be positive. So a can be anything. A can be any real number. So we say that a is an element of the reals because we're just squaring it. So a can be absolutely anything. So now I'm going to simplify. Root 45a squared is the same thing as 9 times 5a squared, which is square root of 9 times the square root of a squared times the square root of 5. Now I'm changing the order a little bit, but I know that I can simplify this. The square root of a squared is just going to be the absolute value of a. So then we have 3 times the absolute value of a times root 5. What? Is that real? Yes, that is real. That is correct. What about this one? The fourth root of 7z. So we know that since the index is 4, which is even, the radicand must be positive. So that means that I'm just going to do this the longer way. 7z must be greater than or equal to 0. I'm going to isolate the z. Z must also be greater than or equal to 0. Done. So we're going to simplify. So remember, step 1 and then step 2. Step 1 and then step 2. Simplify here. The fourth root of 7z, well, there are no perfect fourth, perfect fourth factors in 7, so literally this is as good as it gets. Last but not least, let's do this one. Now we're looking at cubed root. So here we go. Since index is odd, the radical is defined everywhere. Okay, so what I can say is so in other words, the radicand can be both negative and positive. So whenever we see an index that is odd, we just say, okay, y is an element of the reals. Y can be anything. It can be positive or negative. So step 1, done, where it's defined. Step 2, simplify. So the cubed root of, not 3 times the root of, but the cubed root of 24y to the 5. So we're looking for perfect cubed factors. So the cubed root of 8 times 3 times y to the 3 times y to the 2. Because when we have the same bases, we add the exponents. So y to the 3 times y to the 2 is y to the 5. I'm going to move the perfect square factors to the front, and I'm going to leave behind the not perfect square factors. So we have the 8 and the y to the 3, and what we have left over is the 3 and the y squared. The cubed root of 8 is 2. The cubed root of y to the 3 is simply y, and we don't have to worry about the absolute value this time because it's an odd index. And then we're left with the cubed root of 3y squared. And we're done. So what I want you to focus on is the textbook work. You will receive extra practice in 2.2 after the next section.